All right. Our final boss, right? Our last topic will be about the RKN method, very infamous, right? In the department, the RKN method or the Runge Kutta Nyström method. Right? You will see this crop up in other places, right? But this is supposed to be the subject where it's supposed to be introduced, right? But the Runge Kutta Nyström method, right, is a numerical method for second order differential equations. And as you may see, right, it's much more involved this time around, right? It bears a lot of resemblance to the RK4 method for first order differential equations, but this is a different breed completely, right? We will have, right, well, it bears a lot of resemblance to normal uh, numerical methods for differential equations. You will have your equation, right? Your equation, but now your equation will be based on the second derivative. Now notice this is the second derivative, and well, everything in here will be isolated. Sorry, rather the second derivative will be isolated. Everything else will serve as the function itself. Right? We will get initial values, and now you will see that there is an addition here, this x dot, right? If we're talking about stuff like acceleration, say for example, this sounds like acceleration, right? And this can function as your velocity. What you will need is your initial time measurement, your initial displacement, and your initial velocity, if you want to think about it that way, right? You need to get a step size of your h, right, as small as you can, right? And you will follow these 6 iterations, right? Or rather, these 6 steps before you go to your next iteration, right? You will have k1 first, right? You will just get the full function and then you multiply it to h over 2. So you might be wondering now, okay, why is there the need for an h over 2, right? K1 as well as the other k's in here represent slopes, right? That is our what do you call this? That is our agreement as with before, right? And what happens in here is that this now no longer says anything about the slope. This is actually is going to be the rate of change of the slope, or in math terms, that is what we call concavity, right? Basically, if this thing is positive, it's going to be concave up. It's going to look like a smile. And if this is negative, this will be a concave down, or this will look like a frown, right? And so now things get a little bit more abstract in here. That is why we are doing step sizes, right? Note that in this case, if you're now doing h times d squared y over dt squared, you are now stepping, or rather, you are now canceling one of the units downstairs in here in dt squared. Essentially, what you're doing in here is that you are creating your own slope by yourself, right? And just with the RK4 method, what this does is that it takes half steps, right? It takes half steps. Look at this. It takes half steps for K2 and K3, and then it will take a full step for K4, right? And now you might notice the big glaring new thing in here is the appearance of this letter K and letter L. So you might be wondering now, okay, what is that K and what is that L? What that is doing is that is now accounting for the fact that you now have, well, shall we say, 2 layers of complexity, right? Last time we only had 1 layer of complexity in here, but now we have to account for two of them, okay? And so, well, we can just stare at this, right? We can stare at this, and you guys can like take a screenshot of this and just like put it in your Excel sheet for when you're going to have the exam, because, well, this is publicly available information. I'm not gonna hold this back from you, right? The Euler method and the improved Euler method and the RK4 method as well as the RKN method are all public. And plus, you don't need to, you don't need to memorize these things. It would be very unfair if I were to ask you to memorize these things, because, well, they're not meant to be memorized, right? They're meant to be fed to computers, and then you let the computers do the hard work, and then, you will have your equation, right? All right. Let's try the Runge-Kutta-Nyström method, the RKN method, for this equation. Oh, well, we also forgot that this is now going to be your next iteration, right? Notice you will have two new values for your iteration because, well, the time bit is just time plus h, right? Time plus h. What I now notice, what I now understand is that, oops, I used x in here and then I suddenly turned this into y. So let's just turn everything in here into y. There you go. And just like nothing happened. Okay, and now what we will do, we will apply these these new iterations, or rather the whole method for this case. And of course, what we're going to do is we're going to compare it with our initial, right, analytical method. Right, in this case, the analytical method that we can use is, if you want to pause just so you can review for your finals, right? The method we're going to use here is MUC again. I know you used it last time, but that is a little bit of overkill. Right? You can use the linear differential equations in here if you'd like. But anyway, let's try and do method of undetermined coefficients right here. We're not doing variation of parameters. This is well under the scope of method of undetermined coefficients. But what we will have in here is, in terms of the differential operator, this will be d squared y. And this is now 2dy. And then this is plus y equal to 3 sine t. Just like before, because this is non-homogeneous, let's look at this first as if it were 0. You will have d squared plus 2d plus 1. You will see, oh, okay. In this case, we will have d plus 1 squared times y is equal to 0. Now that means that your d value is going to be -1 and another -1, or in this case, -1 repeated twice. This now means that our original equation will have a e raised to -t, right, plus bt e raised to -t. Because this is repeated, you need to add this value of t, rather, so you don't get, so they are linearly independent. That's what we call it. Right now, the problem is we are aware that this is not homogeneous. So what we need to do is we need to account for this now using a guess. That guess would be in the form of c cos t. Let's look at cos first, and then sine d sine t after. The thing about this is, because this is a second order differential equation, the only arbitrary constants are a and b. This c and d are going to be undetermined coefficients that we need to determine ourselves. So what will we do with this? We will, of course, derive this and derive it again, and then put it in our equation. Y prime is going to be -a e raised to -t. This thing is going to be a little bit harder to derive, right? We will have, let's just bring it out, bt e raised to -t. If we're going to factor out the b, we will have this. And then let's just product rule it. This is f, this is g. This will be b times f prime g plus fg. Okay, f prime in this case is going to be just 1 times your g, which is e raised to -t, plus your f times your -g, which is -e raised to -t. There you go. That is your derivative. b e raised to -t minus t e raised to -t. Then plus, we'll just make this, or rather, negative c sine t, and then plus d cosine t. And then last time, we will do -a, so this is now positive a e raised to -t. And then we will do this thing again, minus b e raised to -t. And then notice that this is just the negative of what we just did in here. So we will just do -b e raised to -t minus t e raised to -t. And then this will be minus c cosine t minus d sine. Let's now put all of these guys together and into that equation. We will have, honestly, I know these two, or rather these first few bits are going to cancel out, but we'll see them cancel out, right? We will have a e raised to -t. Note that in here there are two negative b's, so minus 2b e raised to -t. and then plus, right? Plus bt e raised to negative t. And what next? Minus c cosine t minus d sine t. That is your y double prime. Now we will add twice our y prime. We will now have minus 2a e raised to negative t. In this case, you will have plus 2b e raised to negative t minus 2bt e raised to negative t minus 2c minus 2c sine t, and then plus, or rather plus 2d cosine t. And then we will have just our y in here, plus a e raised to negative t plus bt e raised to negative t plus c cosine t plus d sine t. And then all of that should be equal to 3 sine t. So now notice, right, all of these guys get canceled out, right? A, that's plus 2a minus 2a, cancel. Plus 2b minus 2b, cancel. Plus b minus 2b, you cancel that as well. Now you can also cancel a couple of things in here. Cancel here. Cancel here. You will be left with a tiny equation, which is going to be negative 2c sine t plus 2d cosine t is equal to 3 sine t. And well, frankly, you can also create in here a 0 cosine t. That means that all of the blue ones, or all of the green ones and all of the blue ones, should match here. Okay, let's have here negative 2c is equal to 3. That means that your c is equal to negative 3 over 2. And then your 2d is equal to 0. Well, that's no big deal. It's just going to be t is equal to 0. That means our final answer, or not our final answer, but our answer currently, our general solution is ae raised to negative t plus bt e raised to negative t plus c cosine t. That will be now negative 3/2 cosine t, and then there's no d. Okay, so that is our current solution. What about if we put in our values of y0 and y dot 0? Okay, let's try this out. If we put in t equals 0, we will get y equals 1. Yeah. Well, now you will get 1 is equal to ae raised to negative 0. So that's just 0. So it's just 1. Plus b times 0. E raised to 0. All of this gets cancelled out. Minus 3/2 cosine t. In this case, you have cosine 0, which means this is just going to be 1. Hopefully, you guys remember that. And now what you will have is 1 is equal to a minus 3/2, which means that your a is actually going to be 5 over 2. Very interesting. And so now we will go here, right? We will go here and we will just take that as our y prime. Honestly, I can just write down my y prime in here. No big deal. Y prime is going to be negative a e raised to negative t plus b e raised to negative t minus bt e raised to negative t minus, or rather, this is now plus 3/2 sine t. Is that right? Yes, that's right. I'm just looking here so you guys know. Okay. Now we know that your a is 5 over 2. Let's now put that in there. Right? Negative 5 over 2. Oh, sorry, positive 5 over 2. And so now we will put in here, if your t is equal to 0, your y prime will be equal to 0 as well. So 0 is equal to negative 5/2 e raised to 0. That's just going to be 1. Plus your b times e raised to 0. That's going to be 1 as well. Minus b times 0 times e raised to 0. Cancel everything in there. Plus 3/2 times sine of 0. Well, you cancel everything there as well. That's going to be sine of 0 is equal to 0. That means now your 0 is equal to negative 5/2 plus b. Which means that your b is actually going to be 5/2 as well. So that means now our answer is as follows. You just replace your a and your b with 5. 5/2, right? We'll have 5/2 e raised to the negative t plus 5/2 t e raised to negative t, and then minus 3/2 cosine t. This is now our answer. Okay, this is now our answer. And that is our analytical method done. Right? However, we're gonna have to test this against RKN. We already know the stellar track record of RK4, so the RKN should work well as well. Okay, let's see now. Okay, but first of all, I will do a little check, see if what I've done is indeed correct. 5/2, 5/2. Yeah, that makes sense. Yep. Okay. So our solution is indeed correct in here, so that we don't make any more issues the last time, like the last time. We'll just put this in our Excel, and let's just do everything the same way we did for here. We have our DE in here, which is y double prime is equal to, well, let's put everything together now. Y double prime in here plus 2y prime, y is equal to 3 sine t. That means that your function now, your y prime, is going to be 3 sine t minus 2y prime minus y. Okay, so that is now it. 3 sine t minus 2y prime minus y. That is your differential equation. Oh, let's not stretch it like. And then let's have here your x0, your y0, your y dot 0. And yeah, have these. You will have, this is, oh, sorry, this is not x0, this is t0. 0, and let's have here 1 and then 0. And here, of course, we will have our h. How did we order it before? Okay, our h comes first. Your h here is going to be, well, let's try first 0.1. And then we will have our analytical solution in here. X, y, y prime, prime. Oh. Okay, let's have this as t pala, sorry. It's going to be 0 in here. Then our y. Okay, let's have our value of y prime as well. Y prime is going to look like, okay, let me solve this. Let me solve this a little bit. You'll now have y prime is equal to negative 5 over 2 e raised to negative t plus 5 over 2. Oh, they're going to cancel out. E raised to negative t minus 5 over 2 t e raised to negative t plus 3/2 sine t. So they're going to cancel out. That means that this is your value of y prime, and I'm wondering in here because I'm gonna have to put it in here as well. So this is going to be 5/2, so that will be 2.5. 2.5 times e raised to negative t, exponent raised to negative t. That will be b10. Then we add 2.5 times b10 times exponent negative b10 and then minus 1.5 times cosine of b10. Now, the thing about this is that we're gonna have to find out if cosine of pi or cosine or if it uses degrees or radians. Let's try out cosine of 90. Okay, so that's not it. If we try cosine of pi, okay, there you go. So this means this works on radians, which is correct. That is what it's supposed to do, right? And now let's have this y prime negative 2.5 times t, so times b10 times exponent negative b10. and then plus 1.5 times sine of b10. Should be 0. Okay, there you go. Now what we will do is just like before. Okay, our value of h is still c3. Okay, our value of h is still c3, so that's great. So we can just have this again, c3. And then we can keep dragging this down. Well, we can keep dragging both of these down. Let's zoom out a little bit. Go up until 30 again. 4, 5, 6, 7, 8, 9, 30. There you go. Okay, so that is our value, or rather, yeah, those are our analytical values of y, right? Y and y prime, if you want to think about it that. Okay. Now we will go with, we will go with, okay, there you go. We will now go with RKN. And of course, you're going to have a lot of stuff in here. T, Y, Y prime. You're going to have K1, K, K2, K3, L, and K4. You might be wondering, why did I intersperse those two things, right? Or rather, why did I intersperse K and L in between K1 and K2 and then K3 and K4 in this situation? It's because actually it's going to reflect the way that we're supposed to implement these iterations right here. Notice that K2 and K3 require knowledge of K, and K only requires knowledge of K1. So actually, what you're supposed to do in here is first you calculate K1 and then you calculate K. And then you go on and calculating K2, you go on calculating K3, and then notice that K4 needs knowledge of L, and L requires knowledge of K3. So once you get to K3, you calculate L, and then you calculate K4. Then you're able to calculate your y dot 1, the new y dot, and the new value of y as well. So that's how it's supposed to be done. Right? So that is why I'm putting it like this. If you guys want, of course, there's no issue as well in just like going K1, K2, K3, K4, and then K and then L. But for me, I just find it somewhat easier for me to just think through this, because it really does look like it really does look like whatever the calculation is supposed to go through. Okay, so we will start with K1, which is just 1/2 times the step of, right? 1/2 times the step size. Again, I'm locking it here. And then what we will have is the original function. The original function is going to be 3 times sine of t. Sine of t. And then minus 2 times 2 times y prime, which is h10 apparently. And then minus y, which is g10. Okay, so that is your K1. And then finally you get to, or not finally, you get to K, which is going to be 0.5 times C3 times, where are we supposed to go? Okay, y dot, that's going to be H10 plus K1. Your value of K1 is I10 divided by 2. Okay, so just put in here 0.5 times I10. There's your value of K. So it's gonna be a little small. You will see that the values fluctuate in here a little bit, but whatever, right? Just go with this, and then we continue with K2. Now notice everything is gonna be a little bit more complicated, but of course the only thing here, the only thing that's blocking you from just getting through everything else is the first step, because afterwards it's not like you're going to type every single thing after this, right? You're just going to drag it down. Okay, so now we will have t and then y prime. Okay, say for example we encounter t. In this case we will have 3 times sine of t. Instead of using t, we will use t plus half a step. You go, oops, C3. Okay. And then minus 2 times, instead of encountering or instead of using y prime or y dot, you use y dot plus k1, which is I10. And then minus 2 times y. Instead of using, just y pala rather. Just y. In this case, instead of just using y, you will use y plus k. Your k value is J10. There you go. That's how you're supposed to calculate your K2, right? And then your K3 will be calculated much the same way, 0.5 times your step size times. Now we will go through the whole thing again, but instead of using K2 or K1 in here, you will now use K2, right? So this will be 3 times sine of, instead of just t, you will use t plus half a step. Okay. Minus 2 times, instead of using y, you will use, instead of using y prime, what you will use is y prime plus k2. So that k2 value we just we just discovered earlier, we use again. Then minus y. Instead of using y, we use y plus k, which is j. Go. And we will continue. L is now h. Now a full step times y dot plus k3. K3 is going to be L10. And so your K4 finally will be another half step. Then a full step now, right? A full step now. What you will have is 3 times sine of t plus full step. Minus 2 times, instead of y prime, what you will get is y prime plus 2 times k3. Y prime plus 2 times k3, which is going to be L10. And then minus your y, instead of y, you put y plus L. Your y plus L. In this case, that's going to be M10. And therefore, there you go. Those are your values of K1, K2, K3, and K4. And their values of K and L. So finally, we can get to the next iteration, right? The next iteration in here for T is just a step, right? A step. And then you will have in here is Y, which is Y0. So this thing plus H. So your step times y dot plus 1/3, and then you are going to equally weigh K1, K2, and K3. If you're wondering why K1, K2, and K3, I have a suspicion, but I don't know if this is correct, this suspicion, right? I have a suspicion that K4 is no longer counted. Oops. I have a suspicion that K4 is no longer counted because, well, this is why we're talking about, right? If we're going to apply the same kind of logic just like before, right? Our K4 methods only apply this 1, 2, 2, 1 kind of prospect, kind of weighting system to the immediate next value. Or rather to the immediate next, how should we say this, derivative. Note that in this case, we have dy over dx and then y. That is the relationship, the 1, 2, 2, 1 method. But in this case, it's now d squared y over dt squared. Its relationship now is going to be the next closest derivative. That is where you will find the 1, 2, 2, 1 scheme. You might notice, or you might say to yourself, okay, where is the 1/6, right? Actually, the 1/6 is already in here. Note that in this case, right, instead of saying, right, h over 6, right, what you're doing in here is 1/3, and every step, or rather every k in here, has an h over 2 already. So it's kind of an integrated kind of step, right? And then your y prime in here is going to be equal to, y prime is going to be equal to y prime plus, there you go, this is now your weighting step, the very classic 1 k1 plus 2 times k2 plus 2 times k3 plus k4. Okay. And then we can drop down our values here, and then hopefully we can drop down all of our values without much of a hitch. Okay. See our values. Let's see our error for y. We will have absolute value of y here minus here divided by C40. And then you will have your error in the y prime in here. Let's see our error in the y prime. This minus this divided by this. You will see that these errors are small, right? Small in the sense of, wow, that's small. Look at that. Let's see how many. Oh, yeah, look at that. Great. Those values are really small. Let's see, for example, if we turn this into 0.25, those errors are still way small. Even in 0.5. What about 1? Okay, that's too big. The second one. Oh, okay. Let's reduce the. There you go. Okay. So in the case that your h is 1, which is gigantic, if we're going to think about it, right? It is still small. It's still 35%. Excuse me. And well, we try 0.5. There you go. It's in point something territory. And this is percent we're talking about. So the error in here is already in the order magnitude of 10 raised to negative 3, which is small. It's tiny. And if we want, we can actually graph these. So we're going to have to take a step back. And then let's try and insert, excuse me, a line. Or let's just do this, then this, then have recommended charts. These ones. Look at that. That is so freaky. For the lack of a better term, freaky. Do you guys see the blue? Because I don't. Right? I don't. It's so scary. I mean, let's make this 0.75. You will now see that the blue is actually just peeking under the orange, right? Let's give these guys names. What is series 1 and series 2? Let's select the data. Series 1 is your G10, G40. Oh, wait, let's edit this. This is C10 to C40. This is analytical. Analytical. Okay. And then this is going to be RKN. I don't think I have to put those in. Okay, I suppose I do. Analytical. All right. There. So I hope they're happy. Okay, it's supposed to be double quotes. There you go, double quotes. There. Okay. Yeah. So the analytical is the blue under the orange, and the orange is the RKN. Perhaps it would be better if we turn the RKN into a dashed line, just so we see the blue underneath. There you go. And that is very scary in the way that, well, it's supposed to be able to get your values very close. If your H is now 1, you will now see a kind of a disparity that's happening in here, but still, you can see that even in an error of 35%, you're just dealing with, right, 0.23 and 0.31. You might say that's very large, but in fact, if we're going to graph it like this, there's no deal, right? And mind you, this is now 30 seconds if we want to think about it, right? 30, the T, this is now 30 seconds. What about 2? I feel like now there's a little bit of a, yeah, it trails off here. Trails off here. About 1.25. All right, this is already starting to get a little bit a little bit offhand, but still, right? It still follows the main shape of the graph. Right? What about 1.5? I'm so sorry. I'm just looking at here. There it is. There's the runaway effect that we are talking about. Okay. So the runaway effect, right? It's going to start between somewhere between 1.3 and 1.5. Let's try 1.4. I'm just looking here. There it is. I wanted to see this kind of runaway effect happen in real time. There you go. Right? So at some point, it just starts to, well, it starts to become way, way off the approximation or way, way off the actual analytical solution. But in this case, well, that is a gigantic step size. Of course, it's very natural that other methods and other numerical methods like the RKN, basically the RK4, they're going to fall. They're going to okay. Let's see, a 1.4. Yeah, everybody's gonna have trouble with that, right? 1.2, 1.75. Right. So see, the RK4 is the one staying strong after all of these things. 0.5, right? 0.25. There it is. Okay, there you go. Right? So that is a testament to the power of RK4, RKN, or basically the Runge Kutta methods in general. So, well, that is it. Right? That is the entirety of this very condensed version of MEADMAT that I have taught you guys. I'm very glad to have taught this special class. I'm hoping you guys have retained some information here, and I'm excited to have you take your quiz like this in Excel, right? So that you can improve upon your numerical methods skills. Okay, that will be all. Thank you very much, and good luck.